Hi, I'm Shraddha, and I'll be talking about our work on just-in-time learning for bottom-up synthesis. The goal of program synthesis is to help users automate low-level programming tasks. The synthesizer takes in a specification from the user that defines the intended behavior, and it also takes as input a program space that constrains the space of possible programs. It then searches for a program that satisfies the specification and returns it to the user. In this work, we focus on syntax-guided program synthesis, also called SyGuS, where the specification is in the form of input-output examples or a first-order formula, and the program space is defined by a context-free grammar. In this talk, we focus on using examples as spec. The goal of the synthesizer is to generate a program that matches the input-output examples using the grammar. In particular, suppose the goal is to synthesize a program that removes angle brackets from a given string X. The specification for this consists of 3 input-output examples where the input strings contain angle brackets and the output strings do not. The synthesizer has to generate a program that would perform this transformation. In addition, the synthesizer is given a small string grammar which constrains the space of programs to be explored. This grammar has 1 string variable X and 3 string literals. It also contains a replace and a concat operator. Using this grammar, the goal of the synthesizer is to generate a program that involves repeatedly replacing the angle brackets in the input string with an empty string. To better understand the solution, consider the highlighted portion. This part replaces one set of left and right angle brackets in the first input example with an empty string. Because the grammar allows for no loops or recursion, and the replace operator only replaces the first occurrence of angle brackets, the solution involves calling replace 6 times. We assume that the user is interested in processing strings with at most 3 pairs of brackets, so this solution is sufficient. Traditional enumerative synthesizers explore candidate programs in the order of size. To find a solution to our problem, a traditional synthesizer has to consider over 30 million programs, since there are that many programs of size equal or smaller than our solution. A traditional synthesizer we implemented times out after 20 minutes on this problem. One promising approach to speeding up the search is guided program synthesis. This approach assigns different costs to different programs, such that cheaper programs are more likely to be good solution candidates. The synthesizer then explores programs in the order of cost instead of size and is hopefully able to find the solution faster. So in guided program synthesis, instead of using a context-free grammar, the synthesizer uses a probabilistic context-free grammar or a PCFG. For our purposes, a PCFG is just a context-free grammar where each production is associated with a natural number cost. Since this PCFG assigns a lower cost to replace than to concat for the given problem, the synthesizer only has to explore 130,000 programs instead of 30 million and finds the solution much faster. However, there are 2 major challenges in guided program synthesis. Firstly, how to learn useful costs, and second, how to guide search given costs. For the first challenge of how to learn useful costs, existing approaches learn costs offline from a large corpus of data. They require significant amounts of high-quality training data, which must contain hundreds of meaningful programs per problem domain targeted by the synthesizer. Such datasets are generally hard to obtain. To tackle this challenge, we propose a technique called just-in-time learning that uses partial solutions enumerated during search to learn costs on the fly. Partial solutions are programs that satisfy a subset of the input-output examples. They are often similar in structure to the actual solution, and so we use them to learn costs. For the second challenge of guiding search, existing approaches use guided top-down search, whereas we propose a new algorithm we call guided bottom-up search, which is more efficient since it uses powerful pruning techniques. We implement our technique in a tool called Probe that takes as input a SyGuS problem that consists of input-output examples and a context-free grammar. If the synthesis component finds a solution, we return it to the user. If it doesn't find a complete solution, but finds partial solutions that satisfy a subset of examples, these are fed to the learning component, which updates the PCFG on the fly, and probe restarts search using the updated PCFG. Coming back to our remove angles problem, recall that the traditional synthesizer timed out after 20 minutes, whereas probe finds the solution in only 5 seconds. So this talk will be split into 3 parts. In the first part, I'll talk about our just-in-time learning technique and how it uses partial solutions to update the PCFG on the fly. Then I'll talk about our guided bottom-up search technique that enumerates programs in the order of cost. And towards the end, I'll present an evaluation of probe across 3 domains. So let's dive into the just-in-time learning technique. The inspiration behind this technique is that partial solutions are similar in structure to the actual solution. For our remove angles problem, we first consider a uniform PCFG where all productions have the same cost 3. Starting from this uniform PCFG, the synthesizer encounters the first partial solution we call replace 2 that satisfies example E1 since it removes a maximum of 2 angle brackets. From this partial solution, we learn that replace seems to be a useful operator to solve our remove angles problem, whereas concat is not. To encourage the synthesizer to explore programs with more replaces and fewer concats first, we reward the productions that appear in replace 2 and update the PCFG on the fly. Since replace 2 contains the replace operator and the string literals, we reward these productions by decreasing their costs from 3 to 2. This update increases the relative cost of concat. With this new PCFG at hand, the synthesizer begins searching and soon encounters another partial solution that satisfies examples E1 and E2 since it removes 4 angle brackets. Since this program uses the same productions as replace 2 and satisfies even more examples, updating the PCFG increases the relative cost of concat even more. In fact, we have arrived at the same biased PCFG we saw before, using which probe finds the solution in only 5 seconds. Now, to make just-in-time learning work so effectively, we tackled a key challenge with this approach, which is to select which partial solutions should be considered for updating the costs. The search might encounter thousands of partial solutions, and many of them might have irrelevant syntactic features. In our running example, there are more than 3,500 programs that satisfy at least one of the examples. Consider this partial solution that satisfies the same subset of examples as the replace 2 partial solution. We do not want to consider this partial solution because in retrospect, we know that concat is not useful for building the final solution. But how do we determine which partial solutions are useful and which should be discarded? If you take a closer look at this program, you'll notice that it's almost identical to replace 2, except that it adds a left angle bracket to the input string, only to immediately remove it again. This is a very common pattern we observed. Longer partial solutions often contain irrelevant subterms that do not contribute to their behavior in any meaningful way. Based on this observation, probe only learns from the cheapest partial solutions that satisfy a unique subset of examples. In the next part, I'll talk about our guided bottom-up search technique that uses these costs from just-in-time learning to guide search. We first compare the unguided versions of the top-down and bottom-up search techniques. Top-down search explores programs by iteratively unrolling the grammar and gradually filling holes in incomplete programs. At the first level, the starting non-terminal S is expanded into the set of productions. In the next iteration, each remaining non-terminal is again expanded using the set of productions. In contrast, bottom-up search starts with productions that require no sub-expressions. It then uses these programs as sub-expressions for the next level using the concat and the replace operators. The efficiency of bottom-up search comes from reusing already generated programs to construct new ones. Bottom-up search also uses a pruning technique called observational equivalence reduction. This reduction discards programs that are equivalent to some program already enumerated. That is, if they evaluate to the same output for every input in the specification. For example, here the programs X, X joined to an empty string, and this program that replaces an empty string in X are observationally equivalent since they produce the same output on every input in the spec, which is X. So the replace and the concat programs get discarded since they are enumerated later. Now, because each following iteration uses all combinations of enumerated programs as sub-expressions, even a small reduction in programs leads to a significant overall speedup. Existing guided search techniques use guided top-down search. We are in fact the first to combine guided search with bottom-up enumeration. Guided top-down search is similar to its unguided version. It unrolls cheapest programs first, but it uses costs of productions to decide the order in which to unroll them. Instead of using all previous sub-expressions, our guided bottom-up search selectively combines previous sub-expressions based on their costs. Bottom-up search enables us to use the powerful pruning achieved by observation equivalence reduction. Top-down search cannot fully use this reduction because incomplete programs can't be evaluated on inputs. Bottom-up search is very crucial for the effectiveness of just-in-time learning since every generated program is complete and can be evaluated on the inputs. This allows just-in-time learning to quickly compute partial solutions during search. In the final section of the talk, I'll present the results of evaluating probe against state-of-the-art solvers. We evaluated probe on SyGuS benchmarks from 3 different domains: string manipulation, bit vector manipulation, and circuit transformation. These involve synthesizing constant time circuits that are cryptographically resilient to timing attacks. We evaluated probe based on the time to find a solution and the quality of solutions generated. We first compared probe against Euphony, which is the state-of-the-art in guided search. Euphony is our main baseline, and it uses guided top-down search using pre-trained costs. This graph depicts the number of benchmarks solved by Euphony and probe as a function of time. The way to read this graph is for a given time budget, say 100 seconds, Euphony solves 22 benchmarks out of 82 in 100 seconds or less, while probe solves 43 benchmarks in 100 seconds or less. Overall, probe solves 48 benchmarks out of 82, and Euphony solves only 23 benchmarks within a timeout of 10 minutes. Probe outperforms Euphony on the bit vector and the circuit domains as well. So we conclude that probe is faster than Euphony on all 3 domains, despite Euphony having the benefit of pre-trained costs. Next up, we compare probe against CVC4, which has been the winner of the 2019 SyGuS competition. CVC4 outperforms probe on the string domain, but on the bit vector and circuit domains, probe outperforms CVC4. We see that the string domain is the odd one out, where CVC4 vastly outperforms probe. Why does this happen? It turns out that the string domain uses input-output examples as specification, whereas the other 2 domains use a universally quantified first-order formula. We hypothesize that CVC4 is outperforming probe only when the spec is input-output examples, because this type of spec is prone to overfitting. So for the string domain, we looked into the quality of solutions generated by testing whether they generalize well to additional examples. In this experiment, we synthesize a program for both probe and CVC4 using the training examples, and then test whether the program produces the correct output on the testing examples. The accuracy indicates the percentage of testing examples for which the generated program produces the correct output. We performed this experiment on the subset of benchmarks where a testing set was available. Probe achieves 100% accuracy on all the benchmarks. CVC4 has 7% accuracy on the phone 7 benchmark. This implies that it produces the correct output only on the 7 training examples out of 100, representing a complete overfitting to the training examples. These benchmarks are the ones for which probe does not find a solution, but we see that the solutions CVC4 finds do not generalize well. On an average, probe achieves 100% accuracy compared to only 68% for CVC4. Another metric for measuring the quality of solutions is solution size. Size is a surrogate for program simplicity. Smaller solutions are more readable and they generalize well to additional examples. We compared the sizes of probe and CVC4 solutions for commonly solved benchmarks. As seen in this scatter plot, CVC4 solutions are almost always larger than probe solutions, sometimes by 2 orders of magnitude. Specifically, for our remove angles problem, the size of probe solution is 19 terms, whereas the size of CVC4 solution is 380 terms, which is not at all usable. So to conclude, probe outperforms Euphony on all 3 domains, and although CVC4 outperforms probe for the string domain, CVC4 solutions are 2 orders of magnitude larger than probe and do not generalize well. In conclusion, just-in-time learning and bottom-up search work well together. We enumerate programs in the order of cost during guided bottom-up search using on-the-fly guidance from just-in-time learning. We are faster than state-of-the-art in guided search, and the solutions generalize well across 3 domains. Thank you.